Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now if you find my videos interesting and important to your studies, also please don't forget to subscribe. In this video, I'm going to present the discussion on the construction of shear and moment diagrams using the area method. And for the theory and the concept on the construction of shear and moment diagrams, please look at first my video on the relations among the shear, the moment, and the load. Level 36. Construct the shear force and bending moment diagram for the beam shown by the area method. Neglect the weight of the beam. So here is the given figure. Let's call the vertical reaction at A as AY, and the horizontal reaction is 0 as shown. Then at C, R sub C. Summation moment about C equals 0. So we have AY times 4 minus 6 times 4 times 2 minus 9 times 1 equals 0. Solving for AY is equal to 14.25 kilonewtons. Likewise, summation of moments about A equals 0. R sub C times 4 minus 6 times 4 times 2 minus 9 times 3 equals 0. So R sub C is equal to 18.75 kilonewtons. So if you check summation versus Y, it should be 0. So 6 times 4 plus 9, 33. And this is also 33 kilonewtons. So we are now ready to construct the shear diagram as well as the moment diagram. So let's put the reactions. 14.25 kilonewtons, 18.75 kilonewtons. So first, we have to have an upward increase, abrupt increase of 14.25 for the shear. Then the area of this is negative 6 times 3, negative 18. Since this is 0 degree, 14.25 minus 18 is negative 3.75. We connect them with a straight line because the slope is equal to negative 6. Remember the relationship between the shear and the load. So the slope of the shear diagram corresponds to the intensity of the load, which is negative, in this case, negative 6. So 14.25 plus negative 18 is negative 3.75. Then we have a downward load, so negative 3.75 minus 9 is negative 12.75. Then minus the area of this loading, which is again negative 6 times 1, negative 6. So we have a sloping line downward, so negative 12.75 minus 6, because this is 0 degrees, so here first degree, negative 18.75, and that closes because we have a reaction of 18.75. Now for this distance where shear is 0, it is either solved by similar triangles. So let us say x1 as to 14.75 equals 3 minus x1 as to 3.75. Then you can solve for x1. But the shorter way is shear 14.25 divided by intensity of the load. Again, the shorter way is 14.25 divided by 6. Then you will get 2.375 meters. So if that is 2.375 meters, this is 3 minus 2.375, so 0.625 meter. So let's shade first. The area of this triangle is 1/2 2.375 times 14.25, and that is 16.922 kilonewton meter. The area of this triangle is 1/2 of 0.625 meter times negative 3.75, so that's negative 1.172, while the area of this trapezoid, I will leave that to you, it is 1/2 of quantity negative 12.75 plus negative 18.75 times 1, and that is negative 15.75. For the moment diagram, beginning with 0 moment at A, the ordinates, if we describe the ordinates to the shear diagram, it is positive 4.25 to 0. So meaning it is maximum here, and the area is 16.922. So positive slope of tangent is like that. And at this point, it is horizontal. So how will you connect that slope of the curve and horizontal? So of course, it is concave downward like that. So positive slope, 14.25 to 0 here. So connect them with a smooth curve, so it looks like that. And the ordinate here is 16.922. So that's why the slope at here is positive 14.25. Then it's horizontal here. Then connect the two slopes with this smooth curve. So it should be concave downward like this. Then 0 slope horizontal to negative 3.75. That's negative. So how will you connect the horizontal slope and this negative slope? So of course concave downward again. So 16.922 plus negative 1.172 is equal to 15.75. So that's the curve. Then finally, from negative 12.75 to negative 18.75 slope, connect them with a smooth curve, so it is concave downward again. And 15.75 plus negative 15.75 is 0. So it looks like that. So that's the moment diagram, shear diagram, and the maximum. So that's it for this problem, because we are just asked to construct the shear force and bending moment diagrams by the area method. Level 37, construct the shear force and bending moment diagrams for the beam shown by the area method. Neglect the weight of the beam. What are the values of the shear and moment at x equals 6 meters? Determine the maximum bending moment. The maximum bending moment is either positive or negative. Take note of that. But in this case, because the beam is end supported, then we expect positive moment only. There's no negative moment for this case, because the expected bending of the beam is positive like that. So let's call the reaction here as AY and AX, but AX is 0 again. There's no inclined or horizontal load. Then here RB, summation moment about C equals 0, AY times 9, then minus 800 times 3 times 5.5, 1.5 plus 4 is 5.5, minus 1,500 times 2 equals 0. So AY is equal to 1,800 newtons. Then summation of moments about A equals 0, counterclockwise positive. So R sub C times 9 minus 800 times 3, 1.5 plus 3 is 3.5, minus 1,500 times 7 equals 0. So R sub C is equal to 2,100 newtons. Then you check if it is in equilibrium vertically. So let's now construct the shear force and bending moment diagrams. Let's put the reactions here. AY 1,800 and R sub Z is 2,100. So this is the shear diagram, and the shear is in newtons. Take note that X is in that direction. So first, we have to abruptly rise from 0 to 1,800. So there's no change in load in this portion, so that 1,800 remains constant. There's nothing to add. Then minus the area of this loading, which is negative 800 times C. negative 2,400. So 1,800 minus 2,400, that's 0 degrees. So first degree here, it decreases. 1,800 minus 2,400 is negative 600. Then between this point and that point, no change in shear, no change in loading. So it remains constant. Then minus 1,500, negative 600 minus 1,500 is negative 2,100. Then between this point and that point, no change in shear, so this is just horizontal. Then it closes because we have an upward force of 2,100. So let's compute this distance. Again, this distance is either solved by similar triangles. We have similar triangles here. So you may call this x1 as to 1,800. Then this is 3 minus x1 as to 600. Then you can solve x1 2.25. But the easier way is shear, which is 1,800 divided by the intensity of the load 800. 1,800 divided by 800 is 2.25. So therefore this is 0.75. So that's it. Then for the area of this triangle, this is 2025. This one half of 0.75 times negative 600, that's negative 225. The rest are rectangles, so we can easily compute it using our calculator. So beginning with zero moment at A, because this is an end support and it is a pin, so zero moment plus the area of this rectangle, which is positive 3,600, 1,800 times 2, so that's 0 degrees, so it's first degree positive slope, straight line. The slope is 1,800. Take note of the relationship. So this is 3,600, 1,800 times 2. Then we have positive slope, 1,800 to 0 slope. So that is the slope initially. Then the slope here is horizontal. Then we connect them with the smooth curve, which is concave down, of course. So concave down's curve. And the value here is 3,600 plus 25. That's 3,000. That's 5,625. Then from zero slope, horizontal, to negative slope, like that. So we again connect them with a concave downward curve. And it is 5,625 plus negative 225 is 5,400. Then we have a constant slope because the ordinate of the shear is constant at negative 600. So 5,400 plus the area of this rectangle, which is negative 600 times 2. So 5,400 minus negative 600 times 2, or 1,200, is 4,200. And straight line or negative curve with negative constant slope of negative 600, and this is 4,200. And again we have constant slope, which is negative 2,100, and 4,200 plus the area of this, which is negative 2,100 times 2, or negative 4,200, so that makes it 0, and it's straight line. So this is the moment diagram. From the figure, the value of the shear when x is 6, this is 2, 3, so 6 is in between here. Since the shear is constant at negative 600, so the shear at x equals 6 is negative 600. Then the moment at x equals 6 is here, so it is 5,400 plus the area, which is a rectangle, negative 600 times 1. So because 6 meters, so the area we add only negative 600 times 1, 5,400 plus negative 600 times 1, or negative 600, is 4,800. So the moment at x equals 6 is 5,400 minus 600 times 1, or 4,800 Newton meter. Then the maximum bending moment is 5,625 Newton meter, and it occurs at 2 plus 2.25 or 4.25 at x equals 4.25. Remember, we base it from the origin, which is at A. So that's it for this problem. Level 38. Construct the shear force and bending moment diagrams for the beam shown by the area method. Neglect the weight of the beam. The end couple M1 is adjusted so as to produce zero moment at the fixed end of the beam. Find the bending moment M at x equals 4 feet. So this is the figure. So take note that the moment at the left is 0, and we're going to find M1. So the vertical reaction AY RL and 0 RX, then ML, which is 0. First, summation versus Y equals 0. So RL minus 200 times 8 equals 0. So the reaction at the left vertical is 1,600 pounds. Then summation moment at the left equals 0. ML plus 200 times 8 times 4 minus M1 equals 0. Take note, ML is 0. So M1 is equal to 6,400 pound-foot. So we are now ready to sketch the shear and moment diagram by the area method. So let's put the reactions, only vertical reaction because the moment at the left is 0, and M1 is equal to 6,400. So first, we have to go up 1,600, then minus 200 times 8, so that's 1,600, so that makes 0 here. This is 0 degrees, so connect 1,600 and 0 with a straight line of slope negative 200. So negative slope curve is, or line is straight line. Then 0 here. The area is negative 1,600, so that makes it 0. Then there's no change in shear here, so 0 everywhere. So that's the shear diagram. The area is 1/2 of 8 times 1,600, so 6,400 the area. Then for the moment diagram, it begins with 0. The slope of the tangent here is 0 because the shear is 0. The slope of the tangent line initially is 1,600. Then here horizontal, so connect them with the concave downward curve like that. So from 0 to 6,400, then there's no area here, so that means it's constant. Then it closes because we have 6,400 there. So that's the moment diagram. Then let's answer the question on the bending moment at x equals 4. So I'll solve this into two ways. First, because this is parabolic, let's apply squared property of parabola. So that's 4 feet, 4 feet also from the right. And this is the moment at x equals 4. So let's draw horizontal line from this point. So that's 4 feet, and this is 8 feet. Then this moment here is the difference between 6,400 and the moment at x equals 4. So that's 6,400 minus moment at x equals 4, this vertical distance. And the total vertical distance is 6,400. By squared property of parabola, 6,400 minus moment at x equals 4 as to horizontal square, which is 4 square, equals vertical 6,400 as to 8 square. So 6,400 minus moment at x equals 4 as to 4 square equals 6,400 as to 8 square. So the moment at x equals 4 can now be computed. It is equal to 4,800 pound-feet or pound-foot. For the other solution, let's have the free body diagram of this portion up to x equals 4. So positive moment is counterclockwise, that's the shear, counterclockwise. So summation moment about this section, moment at x equals 4 is 1,600 times 4 minus the moment of the load, 200 times 4 times moment arm, 2 feet. So moment at x equals 4 is 1,600 times 4 minus 200 times 4 times moment arm, 2. And the result is the same, 4,800 pound-foot. So that's it for this problem. Level 39. The I-beam supports the 1,000 pound force and the 2,000 pound-foot couple applied to the 2-foot strut welded to the end of the beam. Calculate the shear V and the moment M at the section midway between A and B without drawing the shear force and bending moment diagrams. So take note, we don't need to draw the shear force and bending moment diagram, so we'll just make use of the free body diagram. So this is the figure. We will call the reaction at A as RA and at B, BY and BX. Then summation moment about B equals 0. 1,000 pound force has two components, horizontal, which is 1,000 times 3 over 5, and the vertical, which is 1,000 times 4 over 5. The horizontal component will have no moment at B, so just concentrate on the vertical component. So RA times 3 minus 2,000, then minus the moment of the vertical component of the 1,000 pound force, which is 1,000 times 4 over 5 times 6 equals 0. So RA times 3 minus 2,000 minus 1,000 times 4 over 5 times 6 equals 0. So RA is equal to 6,800 over 3 pounds. So there's no need to compute BY because we are only interested of the shear and moment at the section midway between A and B. So let's draw the free body diagram as shown. And we have to put shear, which is downward, and moment, which is counterclockwise at the section. So this is 1.5. So let's remove that and replace by its components, namely 600 pounds, which is 1,000 times 3 over 5, and the vertical component is 800 pounds, which is 1,000 times 4 over 5. And shear here, and moment counterclockwise. So from the figure, the shear is equal to 6,800 over 3 minus 800. And that's the normal, although not needed. 6,800 over 3 minus 800. So the shear force at the section midway between A and B in decimal is 1467 pounds. Then for the moment at this section is summation moment about here is 6,800 times 6,800 over 3 times 1.5 minus 800 times 4.5. So moment 6,800 times 1.5 minus 800 times 4.5. So the moment at that section midway between A and B is negative 200 pound-foot. So that's it for this problem. Without constructing the shear force and bending moment diagrams, determine the shear V and the moment M at the section 3 meters to the left of the support at A. So this is the figure, because we are only required the shear and shear force at the section here 3 meters to the left of support A. Then we don't need to compute for the reactions and just draw the free body diagram of this portion of the beam. So the intensity of the loading here at 3 meters from the left is, because 3 meters is midway between this end and A, so it is 1/2 of 4, so 2 kilonewton per meter. Let's divide the loading into two triangles. This is the positive shear at the section, positive moment at the section. Then let's divide the loading into triangles. So call this P1, and its distance from the right is 2/3 of 3 or 2 meters. And this is P2, its distance from the right is 1/3 of 3 or 1 meter as shown. So shear plus P1 plus P2 equals 0. So that means shear is negative, negative of P1, negative of P2. Then it is P1 is 1/2 of 3 meters by 4 kilonewton per meter, and therefore it is equal to 6 kilonewtons. P sub 2 is 1/2 of 3 times 2, so it is 3 kilonewtons. So again, shear plus 6 plus 3 equals 0. So shear at this section is negative 6 and negative 3, so negative 9 kilonewton. So mention moment about this section. So moment plus P1 times 2 plus P2 times 1 equals 0. So moment is also negative. So it is P1, which is 6, negative 6 times 2 plus P2, negative 3 times 1. So the moment is equal to negative 15 kilonewton meter. So that's it. That's the technique when we are required to compute for the shear or determine the shear and moment at the section without constructing the shear force and the bending moment diagrams. So take note that we can do so by just purely constructing the free body diagram. And I hope that you can remember that whenever you are told to do so. And there's no need to draw shear and moment diagrams.